Now that we've talked about what equilibrium actually is, now it's time to talk about changes that can occur to an equilibrium system. Because once equilibrium is achieved, a reaction is going to always stay at equilibrium until there's some change to the system that affects the rate of either the forward or reverse reaction. Any kind of change that we're trying to add to an equilibrium, we simply refer to as a stress. So when we're stressing an equilibrium, a reaction is going to respond in such a way. When these disruptions or stresses occur, we can always tell which way the equilibrium position is going to shift in a way that's relative to this stress, and this is known as Le Chatelier's principle. The simplest way to think about Le Chatelier's principle is if somebody is trying to push you over and make you lose your balance, you will respond in a way to kind of keep yourself in balance. If somebody's pushing on you, you'll push back to keep yourself on your 2 feet. Reactions kind of do the same thing. If you add a stress to a reaction will respond in a way to alleviate that stress, or it'll actually do the very opposite of whatever it is that you're doing. So if you're thinking of that, when I show you all these different scenarios of Le Chatelier's principle, keep in mind that the reaction is always going to be responding in the opposite of whatever stress that you're adding to it. So here I have a simple equilibrium, A plus B yielding C and D, and they're kind of color coordinated there, and in my picture, and I also color coordinated them in the chemical equilibrium reaction. So I have A plus B becoming C and D, and then C and D will go in reverse and form into A and B. And the very first picture right here is my control system that's in equilibrium. I have A and B becoming C and D going backwards, turning back into A and B, and the amounts of all 4 of those substances is going to remain the same. However, I'm going to add a bunch of A, and so you see a little weighing paper there at the top of the second picture, and we're dropping in a bunch of A. When a reactant like A is added to the chemical reaction at equilibrium, it's going to increase the frequency of collisions between the reactants A and B. So essentially, the forward reaction is going to speed up, and it's going to go faster and faster. And this will increase the rate of that forward reaction, causing the equilibrium to shift to the right. So anytime you have an increase in the forward reaction is always going to shift to the right. Conversely, if we actually removed a reactant from the chemical reaction, it will decrease the frequency of collisions between the reactants for a period of time, and this will cause a decrease in the rate of the forward reaction, causing the equilibrium to shift to the left. So if I add A, okay, and I'm just going to kind of simply draw this on the picture right here. If I add A, that's going to increase the amount of A. The reaction's going to shift in the direction to alleviate, to bring the amount of A down. And in a way, the concentration of B is going to go down, and the concentration of C and D is actually going to go up. And that's basically the way that the equilibrium works. If I actually do the opposite, so let's say instead of adding A, I had some way of actually decreasing the amount of A. Well, then what happens here is that the reaction is going to respond a way in order to bring the amount of A back up. So that's going to cause an increase on the reverse reaction, and therefore the amount of B is going to go up when that reaction shifts to the left, and the C and D is going to go down. So if I add A, it increases the frequency of collisions between A and B, causing the reaction to shift forward. If I remove A, then all of a sudden C and D are going to have a lot easier time finding each other inside of that container, and the reaction is going to shift towards the left. It's as simple as that. And I got a couple of scenarios to maybe help you think about what actually is going to go on. And you might actually want to try these for yourself here first. See if you can kind of fill them out, and then by pausing the video and then actually playing the video and seeing how you did. So I have this reaction here. Solid carbon and water is reacting in a way to form carbon monoxide and hydrogen gas, but if this is trapped inside of some reaction container, the carbon dioxide gas and the hydrogen can get back together and go in reverse and form back in a solid carbon and water vapor. So what would happen now if I increase the concentration of H2O? Now H2O happens to be on the left-hand side of the equation. So if I'm increasing the concentration of my H2O, that's going to cause an increase in the frequency of collisions between the 2 reactants, the carbon and the water there. And so the forward reaction rate, this one right here, is going to increase, and that's going to cause a shift in the equilibrium. And so the equilibrium is going to shift towards the right-hand side. It's as simple as that. Now, what happens when I increase the concentration of carbon monoxide? Well, the carbon monoxide happens to be on the other side of the equation. So by increasing the amount of CO here, that's going to increase the frequency of collisions between the two products, the carbon monoxide and the hydrogen. And so the reverse reaction, or the backwards reaction here, is going to be going faster for a period of time. And so that's going to cause a shift in the equilibrium to the left-hand side. If I increase the concentration of hydrogen, well, same kind of thing here is going to go on. If I increase the concentration of hydrogen, that again is in the product side. So that's going to again increase the frequency of collision between the products. And so the reverse reaction rate is going to increase, and that's going to cause a shift to the left again, or the backwards reaction is going to be much faster there. Now, if I increase the concentration of the solid carbon, well, if I increase the concentration of my solid carbon, a lot of people would think that this reaction is therefore going to shift to the right. But you have to be very careful. Increasing the concentration of carbon doesn't work because carbon happens to be in the solid phase. Remember, anytime that you have a reaction container in there, the carbon material is just going to be simply sitting on the bottom here, and you're not really increasing the concentration of it at all. You're just making it a bigger pile of carbon that's on the bottom there. So there is no way that you can increase the concentration of a solid. You can just add more material to the reaction, and that doesn't cause any change in the equilibrium whatsoever. It just makes a bigger pile of solid material on the bottom. That also goes for liquids. You want to make a note of that on your flip lesson notes here, that if you have a solid or a liquid in your reaction, increasing the amounts of those substances doesn't do anything to the equilibrium, because they always just sit on the bottom, and they don't actually they're not mixed completely throughout the whole reaction container, and therefore you're not really increasing the concentration. Now the last one here is about decreasing something, and remember Le Chatelier's principle. Anytime you increase the concentration of something, the reaction will shift away from whatever you increase, and it'll shift towards whatever you decrease. So if I'm going to decrease the amount or the concentration of carbon monoxide, that's going to actually increase not the frequency of collisions between the products, but it's going to make those reactants have a lot easier time finding each other, because you have less products for those reactants to actually collide into and have no reaction with. So increasing the frequency of collisions between the reactants will shift the reaction in the forward direction, and so therefore by decreasing the concentration of carbon monoxide, the reaction will shift towards that decrease, and that will be a shift towards the right-hand side there. And that's how concentration affects an equilibrium reaction. Now, as far as temperature is concerned, if you want to actually figure out how temperature affects the rate of a reaction, you have to have your heat term in your reaction. So sometimes that'll just be listed as kilojoules or kilocalories somewhere in the reaction. Or they'll just put simply the word heat. And you got to remember that if the heat is in the product side, the reaction is in the exothermic direction when it's going towards the heat, and it's in the endothermic direction when it's actually going away from the heat. Now remember, according to Le Chatelier's principle, the reaction is always going to try to do the opposite of whatever it is you're doing. So if you try to increase the temperature, it'll cause the reaction to respond in a way that is going to shift away from it. So increasing the temperature will cause the reaction to respond in a way that reduces the temperature of the container. Therefore, the reaction is going to shift away from wherever the heat term is in the reaction. Now, in this reaction on the right-hand side, the heat term happens to be on the right-hand side of the equation. So by increasing the temperature, so on the first picture there, it says if you're adding heat, the reaction will shift away from the heat, and so it's going to actually shift on the left-hand side away from the heat. Or decreasing the temperature, where you're actually removing the heat, will cause the reaction to respond in a way that increases the temperature of the container, and therefore the reaction is always going to shift towards wherever the heat term is in the reaction. So If you increase the temperature, reaction will shift away from the heat. And if you decrease the temperature, reaction will always shift towards the heat. That just makes it real simple for you to remember about temperature. As far as pressure is concerned, you have to remember that the only phase of matter that is affected by pressure is the gas phase. So increasing the pressure on a reaction, so if you're looking at my bottom reaction here with I got nitrogen and 3 moles of hydrogen becoming 2 moles of ammonia gas, increasing the pressure on a container will cause the chemical reaction to respond in a way that actually reduces the moles of gas inside the container. So you actually have to count the moles of gas on both sides of the equation. And over on the left-hand side, we have 4 moles of gas. And over here on the right-hand side, we only have 2 moles of gas. So if I increase the pressure on the container, the way to reduce the pressure is to shift towards less moles of gas. So if you look at the little pictures, the little text that's in blue over those double arrows there, increasing the pressure causes the reaction to shift towards the 2 moles of gas so that it actually will decrease the pressure of the container by shifting in that direction, or reducing the pressure, decreasing the pressure will cause the reaction to do the opposite. It will actually cause it to shift towards more moles of gas. And if this reaction was completely flipped around, then the effect would also be completely flipped around as far as pressure is concerned. So increasing pressure, if you want something simple to put in your flip lesson notes in the margin there, increasing the pressure will cause the reaction to shift towards less moles of gas because it's trying to decrease the pressure. And by decreasing the pressure, the reaction will shift towards more moles of gas because it's trying to increase the pressure and bring it back up. So that's basically how pressure affects an equilibrium reaction. If your chemical reaction you're dealing with has the same number of moles of gas on both sides of the equation, pressure will have no effect on the equilibrium whatsoever. So you got to keep that in mind. If you ever have the same moles of gas on both sides of the equation, pressure will have no effect whatsoever on the equilibrium. Now, what happens when we add a catalyst to a chemical reaction? Well, you got to remember from when we're talking about a catalyst that adding a catalyst causes a decrease in the activation energy. But adding a catalyst to a reaction decreases the activation energy in both the forward and the reverse reactions. So therefore, no shift in equilibrium occurs whatsoever when you add a catalyst to a chemical reaction. All that really happens with an equilibrium when you add a catalyst is the reaction will reach equilibrium faster. So you'll actually increase the forward and reverse reaction rates very quickly, and the reaction will achieve equilibrium, but you're not going to, a lot faster, but it's not actually going to cause a shift either to the left or the right because it drops the activation energy like it does on the picture on the right hand side here, but it drops it for both the forward and the reverse reaction. The most difficult one for students to actually kind of conceptualize is something known as the common ion effect. And if you kind of keep it in its simplest terms, it's not really that hard to understand, but it is kind of a little weird because common ion effect occurs when you have a saturated solution. So here I have an equilibrium of lead iodide, and it's an equilibrium with its lead and iodide ions. So you got saturated solution of PbI2, and it's an equilibrium with the lead ions, the lead 2 ions, and the 2 iodide ions that are all floating around in there. Now the lead iodide, the solid material right here, has a very distinct yellow color to it. And so if I had a saturated solution of it, you would actually see a clear solution of the lead and iodide ions floating around. It's kind of hard to draw in this small little picture, but you would have this yellow pile of solid material sitting on the bottom, and this lead pile of solid material would be dissolving and recrystallizing at the same rate when it's actually saturated, and that's what's happening in my little equilibrium system that I have right here. So you have this little pile of yellow material sitting on the bottom. If you happen to add more lead iodide, it would actually it wouldn't affect the equilibrium at all, because adding more lead iodide is adding more solid material to the saturated solution. And we all know from our solutions unit that that solid lead iodide would simply fall to the bottom and just create a bigger pile of lead iodide at the bottom here. However, if you add something like potassium iodide to this equilibrium, that actually causes more lead iodide to form. Now, if you look in this picture, you'll see that there's those white crystals inside of the little scoop, but as they're dropping those white crystals into the solution, it's actually creating more yellow potassium iodide. The reason that this is happening is because the potassium iodide is like adding more iodide ions to our equilibrium. And we know from Le Chatelier's principle that if I increase the concentration of my iodide ions, it's going to cause a shift away from those iodide ions and make more of my yellow lead iodide precipitate. So if I add a little bit of the potassium iodide, I actually get more lead iodide to precipitate out because it's like adding more of those iodide ions. So this causes a shift towards the left, which will produce more solid lead iodide, which is that yellow precipitate. On the other hand, if I happen to add more lead nitrate, which has also got a white color to it, adding more lead nitrate to the equilibrium is just like adding more lead ions to the equilibrium. This would actually have the same effect because when you add more lead ions to the mixture, that's still going to cause a shift away from those lead ions and cause more of that yellow precipitate to be produced. So it's going to cause again a shift towards the left to produce more solid lead iodide, which is the yellow precipitate that you see. However, if I add instead of a lead nitrate, I actually added potassium nitrate, KNO3. This substance would have no effect on the equilibrium whatsoever because there is no ion in common with my saturated lead iodide solution. So adding more KNO3 would just cause it to simply fall to the bottom and it would cause no shift in this equilibrium whatsoever. So the common ion effect is you'd have an increase in solid material when you add a substance that has an ion in common with it because you're increasing the concentration of one of the ions in that saturated solution's equilibrium. And that ends our discussion on Le Chatelier's principle and stresses that happen to a chemical reaction. So just remember and make a note of this if you haven't done so already before I sign off, is that you have to have an ion in common to have any effect on the common ion effect.